we conclude that if the object is moving pretty fast, then theta is going to be greater than 90 degrees, and the object is going to gain potential energy and in the process slow down. If it's moving slow, then theta is less than 90 degrees, the object loses potential energy and speeds up. The object's moving fast, again, path might be like this. We can verify that any radial line to a point on this path will give us a velocity whose projection on the force vector is in the direction opposite the force vector. So this continues up to a point. Now, if it's not going too fast so that it completely escapes the gravitational field of the Earth, it'll eventually reach a maximum distance and start to come back. And when it does, as we'll see in a minute, the potential energy begins to increase. The projection of the velocity vector on the force vector becomes would now be in the same direction as the force vector, so that gravity would be doing positive work, potential energy would be decreasing, kinetic energy would therefore be increasing. Now, if the object moves very slowly, it's going to lose potential energy and speed up. So it might do something very much like this. Hopefully it misses the Earth, because that would be really inconvenient for the object and anybody that happens to be where it came down, if it's got any size. Okay? For the whole path from here to here, at any point, the velocity, let's say at this point, the velocity would have a component in the same direction as the force vector, so the object would be speeding up. So this is going to go faster and faster until it gets here. But now, let's say it's here, what's going to be the case? Here's your radial vector. Here's your force vector. Here's the velocity vector. Again, the velocity vector has a negative projection, which means any displacement will be in the direction opposite. Will have a component in the direction opposite that of the gravitational force, which therefore does negative work again, and if for this phase of the motion, that will result in a decrease in potential energy. An increase in potential energy and a decrease in kinetic energy. Okay, here we have the same situation as before. We have an object here that has some velocity that's perpendicular to the radial line, so that the only change in velocity in the next instant is going to be toward the center of the Earth, but perpendicular to the direction of motion. There'll be no significant change in speed, but then the change in speed will begin to affect the object, and its position somewhat later is going to be right here. Now, I just arbitrarily chose that. It wasn't too arbitrary. Here's a circle, and this position is inside the circle. So what's going to be the path of the object? Well, it's going to start out in this direction. It's got to curve around to get to this direction. So path might be something like this, running along the circle for a ways, but then eventually getting here. Now, when it gets here, what's happening to its potential energy? Well, we'll draw the radial line, and we can draw a velocity vector, and we can draw a gravitational force vector. We see that the velocity vector has a projection in the same direction as the force vector, so PE is decreasing because gravity is doing positive work, since both of these vectors are in the same direction, and the change of potential energy is equal and opposite to the work done by gravity. So the kinetic energy is increasing. And of course we can see that the kinetic energy is increasing because if we look at the force in the direction of motion, project the force onto the velocity vector, we see that we have a force in the direction of motion, and that's also going to tend to increase the velocity. We want to look at this from the energy point of view, but we don't want to lose track of the force point of view either. So this thing's going to continue to speed up. It's also going to continue to have its velocity change in the direction of the center of the Earth, so that as we go a little further, we might have something like this, a curvature toward the center of the Earth, and at every point on this curve we could draw a radial vector, force vector, and the component of the velocity in the direction of the force, and find that the potential energy continues to decrease, kinetic energy continues to increase. So the path up to this point has at every point the characteristic that the velocity vector and the force vector reinforced. Kind of flatten that curve out a little bit. Let's draw a little bit better curve. Okay. And until we get to this point, when the velocity vector is perpendicular to the gravitational force vector. And I'm making no attempt to draw these vectors with their correct relative magnitudes, okay? Or at least I'm making very little attempt. That labeling of the force vector was not good, so let's just do this, okay? Now, the object moves a little beyond and gets curved around a little bit. Well, we have the same kind of shape we have here. And as that progresses, the radial vector and the velocity vector, it's not a very good velocity vector. Let's try again. So the force vector and the velocity vector now are such that the velocity vector has a negative projection on the force vector, so that the potential energy is again is going to be increasing. And I said again has a projection opposite that of the force vector. I was thinking back to the previous example, excuse me. For the first time here, we see that the velocity vector will have a projection in the direction opposite the force vector. And that's going to continue all the way around to here. Now, since there's no change in the total energy of the system, the potential plus the kinetic, since delta W non-conservative is 0, it turns out that we're going to get back to the same point. It's a little more of an argument to that, and we'll make it when we get into this a little more deeply. But at every point along this part of the arc, the velocity vector will have a projection on the force vector in the negative direction from the force direction, so that the potential energy will be increasing from here out and the kinetic energy decreasing. So on this part, potential energy increases, kinetic energy decreases. So we have what's going to turn out to be an elliptical orbit, where the velocity at this point is greater than at any other point, because after it passes this point, it's going to have an increasing potential energy. We're going to have an increasing potential energy, implying a decreasing kinetic energy, decreasing velocity. Minimum velocity here. We move from this point, we move, as soon as we get away from the point, we start to curve, and we get this situation where the velocity vector has a projection in the direction of the force vector, with the attendant repercussions. Okay, this is an important thing to understand about orbits. And of course, if we had a large velocity here, what we would end up with is an elliptical orbit where the maximum distance occurs way out here and comes back. The orbit would have a similar description to this one, but this point would be like this point where you have the maximum velocity, and this point out here would be the point that corresponds to this one with minimum velocity. So we could have an orbit that looks like this, maximum velocity being here, minimum velocity being here, and at any point between here and here, don't want to draw the whole radial line, but here's part of it. Here's your velocity vector, here's your force vector. We see that the velocity vector has a negative projection on the force vector. Not drawing that very well, but you get the idea. At any point from here around to here, the velocity vector will have a projection in the same direction as the force vector. Its projection on the force vector will be in the direction of the force vector with the attendant conclusions. The last comment is simply that if you hit just the right velocity, you hit the sweet spot between this elliptical orbit and this elliptical orbit, and you do get a circular orbit, and at every point of a circular orbit, the tangent vector has zero projection, the velocity vector has zero projection on the force vector, with the result that there's no work. The sweet spot, circular orbit, for circular orbit, velocity stays perpendicular to the force. Change in potential energy zero. No change in kinetic energy. So you have a circular orbit, constant velocity. So there are the three types of orbits. There's a fourth type. If you go too fast to stay in the ellipse, then you get something else, hyperbola. And we'll talk about that later.